Hello, I welcome you all to this another interesting screencast. The problem reads that the spring of the scale has an stretched length of A. Determine the angle theta for equilibrium when a weight W is supported on the platform. Neglect the weight of the members. What value of W would be required to keep the scale in neutral equilibrium when theta is equal to 0? This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. Alright, so in this particular problem, we intend to use a method called the potential energy method. This is an alternative to the equation of equilibrium method for rigid bodies. So it means we're able to solve this problem using the already known methods of equilibrium. Of course, but we intend to use this one for this particular chapter. If you remember in the previous videos, we are using the virtual work method, which we can also use for this particular problem and still find the same answer, but we intend to use the potential energy method. What is this method? So this method states that the first derivative of our potential energy function with respect to theta is equal to 0. And this particular function is due to the elastic potential energy VE and gravitational potential energy. We can either have both of them or one of them. It really doesn't matter, but we are dealing with a system which is frictionless, no friction in it. And right, so this VE is equal to half the stiffness times the stretch squared, and this Vg is equal to W by Y, which is the height. W is the weight. Okay, so let's pick our datum point. Datum for this particular case, or for this method, mainly we are so much concerned with the weight. Okay, we are so much concerned with the weight. So this is our datum. This is our datum. Let's say that's the point where the weight will be acting, center of gravity. Right, so that's our datum. So let's say this point is our G, and we have the weight acting at that point, the weight W. Okay, so this is and then let's call this as our Y W. Okay, this is what is important. For the spring, of course, we know we can get the Ks, we know is initial length and final length. We're able to calculate that. So let's say our datum is, let's call this point A, is A. It's A. Right, and what do we have? Right, so here, of course, let's find what this YW is. YW is just going to be equal to so let's say this height here, let's say this height here is this height of this block. Let's say this height is H. Okay, so say 0.5 H plus L 2L cos theta. Okay, then let's invoke our equation, and then we have our function, which is a function of theta. This is the potential energy function, is equal to VE, elastic and gravitational, and our VE is just equal to half Ks squared, where our S is just equal to L final minus L original. Okay, and L original is just equal to A. Okay, and L final is equal to 2L sine theta plus A. Okay, right, so therefore the elastic potential energy will be equal to half times K, then times S. S is 2L sine theta plus A minus A squared. This gives us half by K. This is a 4 L squared sine squared theta. Alright, which is finally equal to a 2K L squared sine squared theta. Alright, and then we have the gravitational potential energy, which is equal to WY, in our case is YW. This is just going to be equal to Y W times YW. We calculated it as 0.5 H. We are assuming that this material is homogeneous, therefore the center of gravity is just at the midspan of this particular body of weight W, then plus 2L cos theta. Right, therefore this potential energy is just going to be equal to 0.5 HW plus 2WL cos theta. Then finally V, summation of the two just becomes 2KL squared sine squared theta plus 0.5 HW plus 2WL cos theta. Working out the derivative, first derivative of this becomes just 2K L squared. Working out this just becomes a 2 there, like so. Sine theta. Okay, and then we have cos theta. Okay, then this just becomes a 0. This becomes a 0. Then this other part there is just a minus 2WL sine theta. And we are saying this equal to 0. Right, so 2 and 2 can go, 1L can go, and then we can factor out the sine. So say sine theta sine theta, then we have a 2kl, 1l remains. Okay, and the other one has disappeared. Then cos theta, 2l cos theta. Okay, then minus w, okay, equal to 0. Right, the sign we are factoring out, right? So in the first case, so we'll have sine theta equal to 0, then we'll have a 2kl cos theta minus w equal to 0. So we have two equations. Let me just create so that I work them out on the other side. So let me just collect them like so. I bring them here. So there we are. So one equation there, theta will give us equal to 0 degrees. Then the other one will have cos theta equal to w divided by 2kl. Therefore, theta will just be equal to cos inverse of w divided by 2kl. Okay, right, so worked out the first one. Let's find the second one. So let me write this. The first derivative we found it as a 4. This is a 4kl squared, 4kl squared sine theta cos theta minus 2wl sine theta. Alright, so we can write this using the identity, the trig identity. This is equal to sine 2 theta divided by 2. Okay, this. Okay, so therefore this is as good as 4kl squared sine 2 theta divided by 2. This is easy to work on. Then minus 2wl sine theta. Alright, so once we've done this, then this becomes b prime equal to just 2kl squared sine 2 theta minus 2wl sine theta, and b double prime is just going to be equal to 2kl squared, and then this just becomes cos 2 theta and then by 2. Okay, by another 2 there like this. Okay, right, so this just becomes by 2, then minus this just becomes 2wl cos theta, and this we need to equate it. So we'll say this b prime is equal to 0 at neutral equilibrium. Okay, so therefore we equate this to 0, so we'll say 2kl squared, and let me multiply everything. This becomes 4kl squared cos 2 theta, okay, minus 2wl cos theta equal to 0. So a 2 there, 1 goes there, And then what we remain with, what are we looking for? We're looking for W, so we can write W as equal to, W therefore will just be equal to K L 2KL divided by 2KL divided by W, right? Okay, sorry, divided by, what am I doing? So this becomes W is equal to 2KL cos 2 theta divided by cos theta, right? Okay, and then of course they've told us to say this is supposed to be found at theta equal to 0 degrees, therefore W at 0 degrees will just be equal to 2K L, because cos 0 is 1, so basically this is about it. To find the value of W that will make this system be at neutral equilibrium. Alright, so I think this is about it. There we go, this is about it. Let me just outline my final solution. We have this case at 0 degrees, and then we have the angles here. We have the first one, which is 0, okay, and then we have the second one, this one here, okay, right. So I think this is about it. And I hope the video was helpful. And if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye. See you in my next screencast.